Meow. Okay, I think we've almost got enough people. We'll get started here in a minute.
Hello.
Hi, how is everybody?
Good. Alive.
Well, that's always a good thing.
Usually.
Yeah. A few more minutes here. We'll get everybody in. I'll show you what we're going to do for lab 3.
Excuse me, Walter, I had a question about lab 2.
Lab 3? Yeah.
No, lab.
And that's known as a beam lead pair. Many times when you make MOSFETs in current mirrors, they're made on the same piece of silicon, and they're made right next to each other. So they frequently have exactly the same manufacturing parameters off the mask set. So they're very close to each other. But obviously here in the lab, we're using discrete components. And one thing is, if the two current mirrors aren't equivalent to each other, you'll get a slightly different result than what you predicted from theory. And we want to try to explore that through SPICE at the very least. And perhaps if we can get our supplies working, we'll also take a look at this circuit with our analog discovery modules, vigilant modules. And if we do, we can get that turned in for extra credit. The second lab, which hasn't been posted yet, second part of lab 3, is going to be on basically differential amplifiers, bipolar junction transistor differential amplifiers in current mirrors. And I think I don't have that one quite up and running yet. I'll probably get that before the weekend. And then we'll have the next 2 weeks to play around with these different circuits. So if you already have it, if not, let me take a few minutes pause here and go grab your parts kit, your breadboard, and your jumper wires. And we'll kind of walk through the circuit and get you started so you can wire it up and then take a photo of it. And then by Saturday, or certainly by no later than next week, you'll have it ready to go. And then when I post the BJT circuits, you can also wire them up, design them, wire them up, and have them ready to go next week, even though you won't be able to measure them. At least they'll have some photos and some ideas on what they'll look like. we'll talk about simulating them as well. So let me give you a few minutes here. If you haven't already, go get your breadboard, go get your jumper kit, get your Digilant ready to go. We'll poke around with it, and we'll go through this circuit design here. Have you guys do the analysis, the design, and then pick your components and wire it up. By the way, I clarified with KT on the different kits that were out there, and it turns out most of you don't have anything to worry because he handed out the correct kit with all the analog Digilant discovery modules. And I was the only person that got a kit from Seattle, not a kit from Bothell. So that's why mine was missing things like the 2N7000 NMOS MOSFET. But he knows where I live, so to speak. So he's going to drop one by my house here in the next few days. So I'll have it ready to go for you guys next week as well. I'll be using the same components you guys are using to build up my circuits. And same breadboard, same analog discovery 2 module. And another thing, development, it won't affect you because you're in 332, but it will affect your capstone programs, obviously, next year. But they're already talking about having online classes for the rest of the year, not just the academic year, but for the rest of 2020, barring unforeseen circumstances. Things could change. And it sounds like the University of California system, Cal State, that includes all the major universities and 500,000 students, has already made the decision down in California. And I suspect Washington and Oregon will probably follow suit here in the next couple of weeks and make some announcements. What that means for you guys, probably, if we do so, is it'll be more of the same in terms of coursework. It'll probably be online coursework. And as we've evolved during the spring semester, there'll probably be some changes in the way the classes are taught, office hours are held, and whatnot, just based on learning experience. But in terms of the labs, having gone through this 332 lab and gone through the other preceding labs, 215, 233, 331, and 332, I can now, I'm going to spend my summer changing all the circuits around so that they can all be done with the analog discovery 2 module for 233, 331, and 332, and breadboards and a slightly different parts kit. I'm going to use more modern, newer op amps and whatnot, your parts kits, so we can power them up with lower power. And we're going to purchase, my understanding is the university is going to purchase, I'm putting together an order, some DC to DC converters. And we'll talk about a little bit about that today. Some DC to DC converters to go along with the analog discovery 2 modules. And we'd like to also purchase enough camcorders with tripods to go around to every single student, to be loaned to every single student, and also to have a wall plug for the analog discovery 2. So we'll have the same discovery 2 modules that you guys got used to using, plus we're going to buy some more accessories for each and every one. Mainly, we're going to buy some DC to DC converters to get us to higher voltages on the breadboard, little plugs that I've been looking at. And we're going to purchase also a wall plug that plugs into your power outlet of your analog discovery 2 module, so you don't have to power it directly from the USB laptop. I mean, you're still going to be interfacing to the USB to run all the software, but it'll be getting its power from a wall plug, a wall wart. So this will allow us to do just about every single lab in that series. And the ones that we cannot, like I'm introducing some filters and things like that in lower course levels, early op amps, but I'm going to be using modern op amps. I'm going to have to purchase a little bit more expensive version than the 741. We're going to go to a new op amp, which we can build filters out of a chopper, basically. That's available. That's a modern op amp. It's one of the last ones. It's still in one of these dip packages. It's mostly surface mount, but then we're going to get these for you guys to play with. So there's going to be some changes to the labs. Not that it will affect you so much as the students behind you. And with the advent of the cameras, Joe DeCure and I have been talking, kind of done some demos. We've looked at the cameras, and the webcams are not so much for looking at you. We want to look at your circuits. So what we're going to do is we're going to purchase relatively inexpensive webcams from Logitech, and we're going to look around and find you a tripod. And then, so when we loan out all this equipment in the beginning of the course, like we did this spring, everybody will pick up their package, so to speak, of all this equipment, breadboards, parts, Digilent 2, wall plug module, DC to DC converter, and so on. And then we'll basically, and your webcam, and then we'll basically be able to have labs in real time where you're not just looking at the circuits I'm building, but you'll be able to build a circuit in real time under your webcam. And then after, 15, 20 minutes, after calculating what you need to do and bringing the circuit and building it, you can actually turn it on. And I think if we have that capability, we can actually have online labs with fairly simple equipment. And I'm thinking of pairing students back up with partners. Okay. So that's some of the changes that are up and coming that we've been discussing. The idea is we would have a Zoom lab meeting, like a normal lab meeting, for 2 hours. It would consist of me maybe giving a lecture, talking about the circuit, showing how the equipment was used, and then placing you guys into breakout rooms. And in each of the breakout rooms, you would work with each other on your circuits and have your webcams and things like that, so you could speak with each other and show each other the circuits. And then I would just visit from one breakout room to the next and see how everybody's doing, or you could raise a hand and I could line up the breakout room. So it's going to be a different kind of a sequence than what we did this year. This year was kind of a learning year for courses and labs and everything in general. And based on our learning, we figured out how we think we can do it if we have to do it again from off campus next year online. Some thoughts on that. I think since you guys are in 332, you're pretty much done with your last lab. Knock wood, I hope. I don't want to see any of you guys back. I hope not. I don't know. I guess I'll have to ask Talban. So where this will affect you is I'm also talking to Dr. Talban, Professor Berger, myself, Wayne Kimura, all these capstone sponsors and whatnot. And we're deciding if we get the right equipment, we can probably use the analog Digilent discovery modules for working on capstone programs as well. There we need a little bit higher voltages in some cases, maybe some other specialty equipment, but we're thinking of maybe we can do that for the capstone as well. And they're beginning to experiment with that. So what it'll mean is that your capstone programs may go ahead as planned and have some hardware being built up for the capstone program as well for you to test. And it would still be on a team basis. You would be building one thing, but you all have your own instruments to do some testing, perhaps. So that's what we're looking at. And that's how it will affect you guys probably in the next, depending on if you're graduating this spring or if you're coming out in summer or in the fall. That's how it'll affect your labs and capstone programs. All the other labs are going to be on hold, I believe. I'm still having projects in some classes, but I'm sitting around and thinking that the projects will be simulations only with software, which is okay because there's a lot of that done in industry these days. And I may just deliver some boards to students at the end of the class and not make it required so they can build up their own little circuits and take a look at things if they so desire. So those of you who are in 332, I would say if you're getting ready to take a capstone program and you're thinking about a capstone program, think of it in terms of not only which team you want to join or which project you want to work on, but perhaps if you can, and I don't know how many of these analog discovery modules will be available to loan, but if you can, I would start looking into getting your own and some accessories for it because it'll bide you well, especially if you have no other equipment at home. Obviously, some of you've got digital multimeters one or two of you I've talked to may have, your own oscilloscope or a function generator, maybe a power supply here or there, but the majority of you do not probably have that level of equipment at home, much less soldering workstations and things like that. So if your capstone program is in the near term, I would start taking a look at it, start talking to your capstone advisor, and start thinking of making a purchase, trying to see if you can pick up Analog Discovery 2 module. They have a webinar. Digilent has a webinar on these things. It's pretty good. I'm going to start attending their webinars. I believe if you go to their website, it's scheduled for the Thursday morning at 9 a.m. on the 29th or the 28th of May. And their webinars are getting pretty good because we have a lot of universities now coming in and sitting in on these things, doing things like you guys are doing. And on top of that, Digilent has a stay-home order for their engineering workforce. So they gave every single person a module plus some other equipment, and they're at home debugging their FPGAs. They're doing all sorts of interesting things, and they're going to have webinars on it. So you can actually join for free, go in there and listen and see how it's used by one of their engineers to debug something he's working on. I think those are worthwhile, especially over the next 6 months to a year, to start looking into this, because this is going to be the one tool you'll probably have access to for the time being, until later. Perhaps at work you'll have back to scopes and function generators, or perhaps we develop a vaccine in short order and things go back to a little bit more normal semblance. But I would, for now, it sounds like the engineers in a lot of these workspaces, like Digilent, the electrical engineers, are finding all sorts of fascinating workarounds, and they're using these tools to maximum capacity. And they're giving free information webinars, and that's a great place to learn about these things. That can tell you everything, how they use it, how they use the instruments. They got all sorts of insider knowledge, and these things are free, and you can attend at your own, leisure. And I see the software people doing that as well. So if you're into basically LT Spice, or in my case, I'm looking at Microwave Office. The Microwave Office people are putting out a lot of webinars and information sessions on how to use their software in downtimes. So this is probably, don't let any crisis go wasted, so to speak, and take advantage of these companies are really using this interval to educate a lot of engineers and their tools and their equipment. And that's a very, very useful skill for entry-level engineers to have that. I know that for a fact. One engineer we had, I spoke up for, and Eric and I wrote a recommendation for him. We got him a job at Agilent specifically because he had hands-on knowledge of Microwave Office and had been using the VNA with some projects with us over the summer and coursework. So it got his foot in the door, and he successfully made his way in, and he's now working there full time. So learning people's software, learning their hardware, and doing it even on your own is a very, very, very powerful statement to have on your resume. And as you become an entry-level engineer, that will catch people's eyes. And it's very useful to go participate in some of these sessions and go listen to what these engineers are thinking. How can this Analog Discovery 2 module be used in a lot of different cases for a lot of different testing? And they've got their engineers, and some of them are throughout the globe. The one guy that's giving a talk on FPGAs on Thursday is basically working out of Romania, out of a small apartment. And he's outlined his equipment. The company sent him the Analog Discovery 2 module. He's got an FPGA board, and he's showing how he debugs it and gets everything out of it. And it's just a wonderful class. So, do the legwork, and over the next 6 months, start your own education, so to speak, on some of these tools that will make you much more employable when you do graduate in the coming year. I guarantee it. It'll stick out on a resume. Okay, having said that, let's go take a look at the lab. So you guys got your board, start building them up. If you do have a webcam and you can show me your circuit and how you've done it while I'm discussing it, that would be great. Remember, in the future, if we do this again for future classes, we will probably hand out webcams so you can put one on a tripod and put it right above your circuit while you're building it, and then ask questions and things like that. So we'll have a more interactive Zoom sessions for the labs. But let me go to the course website. Okay, let me share this. Okay, and here's the third lab. There's only one more lab after this, and it's going to cover, we'll see how far we get. We might not get through the entire lab 4. We'll see how far we get in class, but it will cover at least the multi-stage amplifiers. And if we get far enough in class and we have enough time, we'll also take a look at an output power amplifier. So got 4 different circuits, 2 labs, two sections of a report, 3-1 and 3-2. The first section is on MOSFET basic current mirrors, and then we used also take a look at, without tearing it down, use the same one to look at an enhanced Widlar current mirror, and you'll be building both of them and at least simulating them, designing them, simulating them, and then if we get the chance, we'll take a look at the MOSFET with their analog discovery 2 module. And then the BJT is just going to be basically building it on your designing it, building it on your breadboard, simulating it, and then we'll leave it be. That'll be enough for the lab report itself. So the BJT is just going to be basically analysis, design, and simulation with your SPICE modeling setup. So the BJT, we're going to build a diff amp, and then we're going to take a look at differential mode amplifier that's going to be biased by a current source. Okay, so kind of an interesting circuit we'll take a look at next week. So what you need to do now is, if you got your breadboards and your part kit, is we're going to do one lab where we're only going to change one component, and that's to turn it from a basic current mirror to a Widlar current mirror. Okay. So we basically use these guys because in the past you've built discrete amplifier circuits in the MOSFET amplifiers that we built, single stage common source amplifiers, for example. And the amplifiers had basically a lot of components, particularly resistors that were used for biasing, caps that were used as blocking caps, and they were tied to fairly high voltage supplies. Now, in modern design, if you're designing a circuit like that, particularly at lower speeds, at less than a gigahertz or less than hundreds of megahertz, if your circuitry is working down there, chances are you're laying it out to be on one piece of silicon, and you're using a CMOS process. And those are called ASICs, or application-specific integrated circuits. If it's not a company product, it's a specialized component. So when you do that, that's the reason MOSFET technology has really taken off. It's because it's now got what's known as complementary metal oxide devices, which consist of NMOS and PMOS on a same common substrate. And the level of integration is very, very high. And the gate sizes have become very, very small. So it takes up very, very little area and uses very little power. But to do that, you've got to basically throw away as much as you can of those resistors that you were using previously in the discrete components. And certainly the capacitors. You have no room in silicon for capacitors. They're just too big. Okay. So instead, what you do is you use other MOSFET circuits to perform those biasing operations, and also to create your own current sources and whatnot, and differential amplifiers as building blocks. But the whole thing is laid out on one IC using NMOS and PMOS technology simultaneously in a process called complementary metal oxide semiconductor, which is CMOS. And that's the way everything goes. Now, if you look at the 2 basic mirrors out there, there's a third one called the Wilson mirror, invented by a gentleman at Tektronix. But if you look at the 2 basic ones that we're studying in this lab, we're going to use, first of all, we want to discuss this on Saturday. We have 2 different models out there for the 2N7000 NMOS MOSFET. The model that I've posted on the course website is taken from On Semiconductor. and I did some poking around inside the model. And then Dr. Tablian has posted also his own model of the 2N7000, I believe, which is similar to the ON Semiconductor. Maybe even originally it was the same model, but then he's made some of his own changes in there. And what I found on the previous lab, the common source lab, so when I finally got my circuit up and running, when I went in and simulated it with basically using 120 milliamps per volt squared, I found the interesting fact that I did not, I designed it to get a gain of minus 25. It's an inverter, but I did not get that. And that's what many students reported back as well with theirs. Now, my 2N7000 was picked from a parts kit I had 4 or 5 years ago, stashed away someplace. I was not using the same ones that you guys had. So I thought maybe there's some differences there, but then I heard people coming in also and getting maybe as high as 20, 21 gain, but certainly not the 25 they anticipated, minus 25. So what I did is I went into the ON Semiconductor model and I just looked at 3 basic parameters. I played with the threshold voltage over a range, and then I played with the early effect, basically lambda, and I played with the Kn, that design transconductance. And what I found was in the model that ON Semiconductor used, which was the manufacturer of the 2N7000 MOSFETs, was in their model for those 3 numbers, they defaulted the early effect to being an infinite voltage or 0, in other words. And then they basically set the threshold voltage to 2.23 something in the original download. And then interestingly enough for me, they had the Kn set to 0.093, which is quite a bit lower than what I thought it would be. And I don't know if that's just an artifact of something they produced a long time ago, or maybe they take into account somewhere in their model for that effect. But what I did was I ran the same circuit I had without changing the Q point, without changing the resistors, and I ran it, simulated it with that 0.093, and I got almost identical results to what my gain was. So that alone was the most sensitive parameter for me, those 3 knobs, giant knobs to tweak on for that FET. So in this lab, we are looking at these 2 NMOS devices might not only be where we think they are at 120 milliamps per volt squared with a threshold voltage. I guess this wasn't too bad, around 2 volts. They might be over a range, and here we're suggesting maybe from 120 milliamps to volt squared to 180. Some people have reported 150 in their designs when they measured it in 331, for example. And the range of the threshold is from 1.8 to 2.2. Yet some people have used as low as 1.0 or 0.9, I've heard even in some cases. So bear in mind that there's going to be a range and no 2 NMOS devices will be the same. Now, hopefully, if we got them all at the same time and you got your kits ready to go, then they all came from the same batch from the same manufacturer. But that doesn't mean that the 2 NMOS devices that you have to be equivalent to each other. They might actually have different KNs, VTNs, and basically different, even a different early effect could be slightly different. So what we want to take a look at, we want to flush out in your SPICE simulations, is as you're designing this, is to play with how far off your design will be if you start tweaking those numbers over different ranges. In other words, keeping them the same for both diodes and move through these ranges to see if that gives you how that influences your current source, basically. And also to take a look at what if these 2 NMOS devices don't have the same, they're not mirrors of each other. They don't have the same parameters. And so you can start playing and increasing offsets between these when you do your simulations between the parameters and see how that affects the current mirror. And you can see right away it's going to play some havoc with building a good current mirror. And that's why most of these current mirrors, when they're built on the same chunk of IC space. Okay. So, but just bear in mind, we're going to have a range here. We're suggesting numbers of VTN of 2 volts, KN 150 milliamps per volt squared. These numbers I got from Tablian. You want to try with an early effect voltage of 50 volts. But these two numbers can vary quite widely. And we'll see how much they vary not only over batch to batch, but perhaps even within your kit between components when you hook up your mirrors. So basically what we're building here is a basic current mirror with these two NMOS devices back to back. They're tied together down here. And what you're trying to do is you're trying to create a current source from a reference current here. So you've got a reference current source, and then you're trying to design a certain current here. Okay, so you'll go through the equations, and you'll basically assume that both of these MOSFETs are in saturation mode, then they're active mode, and that Q2 mirrors Q1. Now, that's the big assumption you have to make that might not be true. And hence, the circuit's called a current mirror. So you want to design your circuit in 3 based on what you've covered in class to obtain a reference current of 80 milliamps from a supply of VDD1 of 7 volts and VDD2 of 5 volts. Now, when I first looked at this, and I haven't fully explored it, I said, okay, well, I wanted to make one of these labs so it's doable right now on the current analog discovery digital module. So we could do it and test it, actually, see what it looks like compared to the SPICE simulations if anybody wants to get the extra credit. But I'm thinking our supplies go from 0 to +5, and from 0.5 to +5, and from -0.5 to -5 volts. But the more I thought about it, I think we can back-to-back piggyback these two supplies together, and that's something we want to try today. We'll power up our Discovery 2 modules. We'll use the same, since not all of you have a voltmeter, we'll just use the voltmeter that's provided on the Discovery module, and we'll play with the supplies to get them hooked up to a plus minus minus plus, basically, or and back to back, so we can produce a total of 7 volts from rail to rail, and then have a tap in the center where we can pick off 5 volts for the other port. So we'll see. Let's play around with it and see if we can do that, and see if the module's tolerant of that, because it's got 2 separate grounds. So we'll be tying a positive to ground. We'll see how that works, or if it shorts out the supply. So that's one way. The other way is if we can't get that to work, maybe I'll go back and take a look at these 2 numbers, and I'll adjust them so you can achieve them on your MOSFET with the 2 supplies you have. In other words, if we can't get both 7 volts and 5 volts from the 2 supplies we have, the 2 programmable supplies, we'll see if we can basically use a circuit that will require maybe 5 volts and 3 volts as opposed to 7 and 5, and see what we get. Maybe it'll end up with different resistors, obviously, but you can probably use the same 2 MOSFETs. So we'll change the design parameters. Either way, this is the circuit that we would like to design and actually build and measure. So I would go ahead and start working on your design, building your circuit, and then when you're done, just take a picture and hang on to it, and get ready to use the Digilant 2. If you want to move ahead, you can use it certainly before we meet the next time. But let me go ahead and power up the one I've got, and then we'll play around with the rails and see if we can get a 7 and 5 volt supply to the two different drains of the 2 MOSFETs in the current mirror. Finally, the last section of this lab, you're not changing anything except you're going to redo a design, and now you're going to add another resistor R2 down here, a different resistor R2 down here, to achieve the same current. But what you will see with the new design is that the small signal parameters of the current, this is an ideal source for 2 reasons. When you go to integrate these things on silicon, first of all, you have very small signal parameters, basically. So this ideal current source needs to have an infinite output resistance, which is not the case of the basic current mirror. So by introducing this Vidlar configuration, and I believe Dr. Tablian went through this in class and did the analysis from the pi model, I believe it was, small signal pi model, looking back into this, and you found basically the output current as a function of the input and basically transfer characteristic Vs. And what you found was that you had a very, very high impedance being multiplied by the transconductance gain factor. So this has the additional advantage that has a very, very high output impedance, and the resistors you use to achieve the same amount of current, basically, are much smaller. Now, if you remember, to achieve a resistor on silicon is not trivial. It takes up real estate, and it can take up a lot of real estate, and it can scale with the size of the resistor. So if you need 10K, for example, as opposed to 1K, or 1K as opposed to 100 ohms, you have a 10-fold increase in resistance. Sometimes you can have from 10 to 10 squared distance of space required for that additional creation of that additional resistance. So you can see designs are usually any design that keeps your resistances down, the resistances on your CMOS circuit down as small as possible is hugely beneficial. That's why these two improvements, the Widlar and the Wilson, are both slated to be used in integrated circuit ICs to improve and minimize the real estate and minimize the power required to power those, create those circuits. And then basically you can build more sophisticated integrated ICs on with that technology. So we want to look at these two configurations and basically measure them and simulate them. And today, let's pull out our, as you're building your circuit, I will pull out the Analog Discovery 2 module, and I'll just poke around with the supplies to see what they do, to see if we can get that +5 and +7 volts by somehow tying the two 5-volt supplies together and then creating a bus line where we can tap off one bus and another bus to get +7 and +5. Okay? So let me go here now, and I will put up the screen where I've got my Discovery 2 module hooked up, and I'll show you how I'm doing it. Do the same thing at home. Let's see, let me get this guy running first. Pivo. There we go. So they're focusing. Okay. Let's push this out here. Let me share that now. Okay. So everybody see my circuit?
Yep.
So everybody got their own circuits too out? Useful time.
Yep.
Not just listening to me talk, but if you got your Analog Discovery 2 module out, you can kind of follow along. And we might experiment with the breakout rooms. I'm thinking maybe for Lab 4, why not experiment? I'm going to give it a try, see how it works. For the last lab, maybe. So what I'll have you guys do is to go into breakout rooms, pair up and go into breakout rooms, and then we'll see how that works out. Then we can kind of go through your circuits, and those of you who have the capability, since we haven't handed out all the webcams, but if you have a webcam that you can point at your circuit, we'll take a look at it that way, and maybe create groups of 2 or groups of 4 into these breakout rooms and see how that lab works out, that last lab. And I'll see if I can rewrite it so that we can use the digital module for that lab as well. Okay. Anyway, so if you remember, we wired up our pins according to this pin headers, and we basically followed the scheme that we had coming out of the Digilant Analog Discovery 2 module, and basically the first 2 pins on either side, the ones that are solid color coded, orange and blue, with black as the ground, and this is orange and blue with a white stripe on them with black as the ground. I put them on opposite sides of the header, and I basically plug them into the board, and then I can bring this over to my supplies or whatever I need to create voltage supplies or function generators and use these modules. What I've been doing is I've been using, you probably have the same types of wires. Instead of using the jumpers, I've been using these jumpers that have the sockets with pins sticking out of them. They're a little bit easier to manipulate, and they're a little bit longer and more robust to get from one point to another. So you can use them like a probe system. So what we want to do in the system, and by the way, if you do get your own Analog Discovery 2 module at some point, I would strongly recommend getting their breakout header. I think it's only $19 or something like that. And it's basically got all these pins all lined up with one ribbon cable that goes into the module, where you don't need these guys here anymore. You just plug in the whole circuit board, and now your entire circuit board is attached to the rest of your board, and then you can just bring wires over. So it gets rid of some of this harnessing and these separate pins that you don't have to use. But if you do, it's worthwhile taking a look at it. I'll see if I can dig one up here for you and show you what they look like. Makes life a little bit easier. So anyway, what we want to do is we want to take a look at this V+ power supply relative to ground. And we've got a V- power supply on the opposite side relative to ground. And it ranges from -0.5 to -5. And on the top, it ranges from +0.5 to 5. And what we want to see is, so we're trying to get, let's see, where was that number? I know it was 7 volts and 5 volts. Yeah, 7 volts and 5 volts. So can we set this guy, let's say, to -2 volts, and this guy to 5 volts, and then tie the minus polarity or the ground to this guy and not short him out is the question. Can we tie it up like we would a floating power supply? Are these guys floating enough where we can somehow tie them up and create one bar that's at 5 volts and a second bar that's at 7 volts relative to a common ground? Well, let's play with that, and then we'll use our scope. So we'll use our channel 1, basically positive and negative leads as a voltmeter, and we'll probe around there to see if that's possible or whether it's not. If it's not, I'll go back in and I'll create some new numbers for these supplies that will be within the range of the 5 volt and 3 volt supplies. But again, if it's not, we might have some problems with getting 2 positive supplies. So that's what we want to try to have this arrangement. So let's do this. I'm going to disconnect everything I had previously. I was using it to measure my common source amplifier. Let's now pull all these wires out for now, so I can see power supplies themselves. You can even take out the function generator. We're not using it now. Don't really need it. And let's play around with this guy to see if we can do what we want to do. So we'll pull out some of these jumpers. Come back in later, configure them. Okay. What we're hoping to do is, let's use basically the voltmeter. That'll be my one probe from my voltmeter. Okay. And then we'll give it on the opposite side. We'll use a black lead. So this is the plus and minus of my voltmeter. And now let's take the positive supply and tie that to basically a rail. Let's take the negative supply and tie that to a rail. And then let's take the difference between the two rails, +5 minus a -2, to see if we get an overall basically 7 volt supply. So let's do that first. Let's plug this guy in, which is 1, 2, 3, 4. I'll make that a red wire. 1, 2, 3, 4 on this side. I want to go in there. Where's my tweezers? Bad boys don't want to. Okay. There we go. Okay. So 1, 2, 3, 4. Let me bring that ground over on that rail. Maybe this one here. Okay, so that's my negative volts. Positive, and then the other side do the same thing. One, 2, 3, 4.
Can I ask a question?
Sure.
So are you connecting the supply to the red bus and the ground to the blue bus right now on the breadboard?
Oh, on the bottom down here?
Yeah, is that what you're
See.
doing?
Yeah.
Okay.
Basically, I've got this is my negative supply. And
Yeah.
I've got it to the blue line here.
Mm-hmm.
And this is my ground pin.
Yeah.
It's a reference. And I've got it to the red supply line here. And I'm going to do the opposite.
Oh, okay. Okay.
It's actually it's one column over. Right. This one's tied to the blue right here. And this one's tied to the red here.
Yeah.
Okay. And I'm going to do the opposite on the other side. So I'm tying. That's why that breakout board is a lot easier to see. I think I'll use it the next class. Just I know you guys don't have access to it, but then it makes it easier to display what I'm doing. Let's see. We want to get this guy going here. So let's great. Now that's going to be my ground. It's going to be 1, 2, 3, 1. Did I already mess it up? 2, 3, I did. I'm in the wrong place. 1, 2, 3, 4. Okay. Now we'll go to number 3. Smaller wire than that one. Let's see if I got something a little smaller. Smaller jumper. And that will be 1, 2, 3. I'm just seeing if I can float these guys somehow from each other, or whether the grounds are going to be attached in such a way I cannot. That's what we're going to experiment with. Okay. So I'm going to now go and turn on my Analog Discovery 2 digital module. By the way, if you sit in on the webinar at Digital this 29th or the 28th, if you sign up for it, that's my question to them. How much, if I wanted to create all sorts of different supplies, floating supplies and whatnot, and I wanted to boost them up to say plus or minus 15 volts anywhere. So I basically have a variable programmable dual volt supply that can be floating or not. So that was my question for the input to the webinar, and I'll see what they say. Okay. Or some way I can program it in, dedicated ground, in other words, or something like that. We'll take a look. We'll see what they say. So let me go here and power up my Digilant module. Waveforms, start running it. There it is. You guys can't see it yet. Okay. So let's go here now. I'll share this with you. Okay. So everybody see my waveforms up and running?
Yeah.
Okay, good. So let's go back now to the supplies. And what I'm trying to do is I want to set that rail relative to that ground bar is going to be 5 volts. Okay. Now the other one, we're going to set to minus 2 volts. Okay. So now let's see if we can use those two to create our 5-volt supply, which we obviously have, and a 7-volt supply for the same circuit. Let's go here. And first I'm going to measure to confirm my voltmeter that I'm at. So let's go ahead and enable that. Supply is now on. I want to go back to my scope leads and turn them into voltmeters. I'm only going to use channel 1. So let's go ahead and run it. It runs RMS up to 2.04 kilohertz, so that's at 0 now. Let's double check it. I'm going to put it on one ground rail and measure if that's 0. So it's pretty darn close. Just a real small offset there. That could be some new noise. 22 millivolts. You know, now that I'm looking at that, that's interesting. So I have my voltmeter, my 2 channels of my voltmeter attached to each other. Channel 1 positive and channel 1 negative. So I should be seeing 0 volts, right, in theory. I am for AC RMS, but I see a background DC offset between those 2 channels. And remember I was poking around with my scope and I kept having this slight offset problem with my scope. I'm wondering it's somehow built into those 2, because those are the 2 channels I used for my scope as well. I'm wondering if there's a voltage offset between those 2 scope channels, positive and the negative channel. Well, that's interesting. I'll have to play around with that a little bit more. Maybe I just want to use scope channel 1 relative to a ground, but let's keep going anyway here. So that's right now the 2 leads are tied to the ground of the bus bar. So now I'm going to go over and measure the negative rail. That's minus 2.026, minus 2.027. And now bring it over and see if touch those 2 leads together. They should be at the same potential. Again, they're offset by just a little bit, by minus 21 millivolts. Now, let me go back to my original ground and measure the 5-volt supply, which is over here. And that's at 5 volts. How about the other ground? Slightly lower offset. Okay. So now let's flip the leads around. Let's go here to here. I got positive 2 volts. Okay. So now let's think about this. that could be, what if I now tie, but I think those two grounds are tied to each other. What happens if I disconnect that ground and see what it looks like? So it would be from there all the way to there. There's my 7 volts. Okay. So if I attach, and let's see, I set 7 volts relative to that pin, and plus 5 volts relative to that one. Now what happens if I start pulling out the grounds and I attach them to each other? Okay, still 7 volts difference between the two. Pull out the other ground. Still 7 volts. Okay, so these two supplies now are floating with a 7 volt difference between the two of them. Okay. So now what I want to do, so I could use that for one of my inputs. I could attach that from there to the there. But then for my other input, so let's see, that would be plus, we have plus 5. So we need to go from a reference, and that could be from, let me use the other two channels of my voltmeter. And see if I use, so now I have the two supplies are floating, right? And the voltmeter is telling me that between the two supplies, I have a total of 7 volts. Okay, so I should probably draw this for you guys or show you but let me attach the other voltmeter and see if I can get basically a separate 5 volts that would share a common node. So let's see if I have this across there. Now, could I put the node between them to a location? Let's take a look at this. Let me get another voltmeter going here. Okay, there's one lead. Let me get another, maybe a green lead, another black lead or something. No, green one would be good. Okay. Some supplies are floating. So let's measure technically if I got plus 5 volts between there and ground. So I've got this guy here. Oh, that's ground. Let's see. So now what I want is this guy here. Okay. So now I got there to there. Yeah, I think I can do it. I think I can float them. Let's see now, where would the source be attached to? Source would be attached to a common. Would that influence the circuit? Well, I guess we could try 2 resistors. Don't have to build our circuit just yet. And then measure the voltage across the 2 resistors and have them hooked to a common node. So let's put 2 resistors here. I can probe around. Let me bring that one over. So this is going to be my plus 7 volts relative to that. Be a resistor here that's plus 7 volts. Okay. Let's see if I can use that supply as a floating supply. So I'm going to put a resistor across there. Okay. That's that one. That's from there to there. Put another jumper here. Let's see what I've got here. Use this guy here. Okay. Now, I basically have, I believe, 7 volts across that resistor. Let's test that. Yes, I do. Okay. So now let's create a parallel resistor. That will share a common, and we want the common to be, let's see, plus 5 volts to there. So that will be from here to here. Let's get another resistor. Oh, there it is. Okay. One more resistor. Okay. So let's put my voltmeter. It's number 2. It's there, which is 5. There to there. Okay. Let's see, I've got that one there. That's minus, plus. Be that one to ground, so I'll need to create a ground. See if anything changes here. Up in the ground. Okay. One last connection. See if this works. Okay. So let me measure that's the voltage across here. Now if I go across here, 5 volts. Okay. It appears to me like I can float these. Okay, that's my 7-volt bus line. Comes in there. Not clear whether that's really, listen, let me think about this for a second. That's my 5-volt. Those guys would not share. Yeah, I don't think this configuration is going to work. I'm going to try a different one. So what we're looking at here, let's go back to our circuit and take a look at it. Where is that circuit? Here it is. Okay. So let's see, VDD1 is, back circuit, is, back up here, VDD1 is 7 volts. Create that tying supplies up back to create the 7 volts. I think we could, if I'd done it correctly. Let's see. If I put my 2 supplies opposite each other as if they were floating. So I'd have 7 volts from one rail to the next. There'd be a ground in between the 2 of them. And then I could tie the ground let's see, between the 2 of them down to this common pin. And that would give me, let's see if I did it correctly, that would give me +5 minus a -2. That would be tied to VDD1. Then I have a +5. So these 2 terminals would be tied to the W, the -V supply side of the supply. Yeah, I think it'll work. You guys see what I'm trying to do? Is anybody trying it right now? Anybody got their Agilent Discovery 2 module up and running?
Yeah, I tried but failed.
What I'm trying to do, let's see if I can draw it on a piece of paper. Let's see. Okay. So this is my here. Oop, wrong way. See if there's my reference. Okay, it's tied here. This guy's tied here. They're tied together. Common node. Let's just see if this will, in theory, works. So then I have this guy. Let's see. Yeah, I don't think they're floating. Let's see. Let me take a look here. So this is actually I'm gonna drop a little bit. This is +5 minus 5. Okay. Well, this is 2. This is backwards. This one here is +5. That. And then I could tie this one here, 7, Q2, Q1, B2. W1, V minus. Yeah, as long as all the rails are connected together. Let's see, so that one would have to be plus. Yeah, it looks like it would short it out, but let me try it in my circuit here. So let's go from that reference, which is ground, to plus. Let's do that. That might work. Okay, so yeah, I want to go all the way over. So what I need is another green, white for that one. One away. White. Those guys out. Let me go back to my instrument. This new circuit. Share this. Okay. So schematic, I'm going from here. It's going to be my common for both of them. So I need that plugged back in. I think the minute. So let's go from let's go to 5-volt supply. quite seeing it yet.
Well,
Yeah, I'm gonna give it one more try here, and then
I think your supplies aren't on.
I think they're on. I think I'm shorting them out. Now let's take a look. Oh, they turned off. I wonder if they turned off when I shorted them out. Let's take a look. Oh, because I got my toolbar there in the way. Okay, so let's turn this on. I'm kind of curious if I hook that one, which is ground. That's V plus to that ground. So let's see what happens here. Let me unplug everything. Okay. That to there. Okay. Yes, cannot do it. Let's try that one more time. One more time. Here, I have to be able to attach that to the other post. Which is here. So I go through +5. That's there to there. From +5. Yeah, I think it's gonna short it out. There it goes. Yep. Okay, so much for that idea. Can't float them like that because all the grounds are tied. Okay, so I'm going to have to rethink the circuit and use don't see an easy way to do this because all the grounds are attached to each other. None of these supplies are floating. Yep, we need two positive supplies. Anybody see a simpler solution maybe? The problem is the two supplies share the same ground. They cannot float, which means I can't have a +5 supply separate from a -2 supply and hook the terminals together. Hook the negative terminal to the positive terminal. Let's see, is there a way I could do that so that would be ground? Nope, I don't see it. Unless there's something in here. Let's take a look in the help. Supplies. Oh, positive, negative. On, show me the master switch is on and supplies also enabled.
Why not just redefine your ground as the negative power supply? Make that be the common ground for the circuit, and that way your actual ground can become one positive supply, and your B plus will become the other.
So wouldn't we need the positive supply for VDD2? And then we'd add yeah, that's what I'm trying to I guess I don't see the I think both supplies need to float to do that. See what I'm saying? So if I use define the ground as the ground. So let me go back to the circuit. I was just looking at these supplies. On when master switch supplies also pull through find let you adjust values, selecting value from the combo box and typing in or adjusting. Show positive and negative channels. Yeah. I mean, I can see how to get a positive 10 volts, basically, which you just go from the bottom of one supply to the top of the other supply. But the minute you try to create two independent supplies out of that, there has to be a reference. And basically, the minute you attach it to a reference, then one of those supplies is going to be shorted, I believe. Yeah. See what I'm saying?
Could I see the circuit once again?
Yeah. So let's put the circuit up here. I would think they'd have a way of floating the supplies, but I could be wrong. Let's take a look here.
You mean like isolating them completely?
Yeah, where you can tie post to post. and the ground's a separate, you know.
Unfortunately, I have not found a way to do that, but you can use either the minus supply or the plus supply as a common instead of the ground. If you wanted like two positive supplies, for example.
Right.
So
You could
say, for example,
you could
let's
flip
say
them
for-
around.
Say again.
Well, but I think that's let's try that. Let's take a look at the circuit here. Let me see if I can pull it up. Maybe I'll draw it on a pad. Here to the circuit. Where did I have it displayed? Oh, here it is. Okay, let me share this. Yeah, let me zoom. Yeah, so I can see if I tied the supplies back to back and measured from V minus, differentially from V minus to V plus, I could get anything from 1 volt up to 10 volts, right?
Yes.
But I don't see, because now, so for example, if I had -2, see what was VD2? Let's just take a quick look here. Yeah, VD1, 7 volts. So if I had a +5, and then I flipped around and had VD2, that would give me 7 volts around here, at here, right?
Yep.
But now, if I attach this and this guy to common.
So you want the VD2 to be 5 volts, right?
Yeah.
So why not set ground to be -5 volts? VD2 can be ground, and VD1 would be +2 volts. Basically, just subtract 5 volts from all of the voltages in the circuit, and the operating condition will still be identical.
Oh, I see. Setting it down here. Yeah. Okay.
Yeah.
I think, is there any reason why that wouldn't work? Because it's going to be the same voltage drop across here. So the total voltage from here, yeah, because that's the total voltage in your mirror. Yeah. Yeah, so I see what you're saying. So bring this down to -5 volts.
Yep.
And then bring the other supply across here, and then set this to 0.
Yes. And essentially, you're just subtracting 5 volts from all the nodes in the circuit.
Right.
So
right.
VD2 becomes the new ground,
right.
essentially, and the original reference becomes -5 volts.
And let's see, will that change? Because this guy's going to be at -5 volts here. So this is going to be, okay, the drop there, that minus that drop. Yeah, it shouldn't change, should change the current, should be okay. Yeah, so it's lowering the overall circuit all the way down. Might work. I think it'll work. Well, we'll give it a try. Let's see, -5 volts there. What's that going to do to there and there? So that's going to be all the way down. That's not going to change. That's not going to draw any current, so they should be equal. It's going to be 0. That's 5 volts. Gate's going to be on. Okay. They should still have the same current. That should set up the reference current. Okay. Let's see, so that would be okay. 2. Yeah, okay, I think it'll work. I don't see why it wouldn't. Let's give it a try. Let's hook in there. Get my MOSFETs in. Okay. Into my circuit now. +2. Okay, 1, 2. Yep, let's get that one there, that one there. That's going to change this guy. Go back here to my supplies. So this will be +2. Okay. Let's get them running. Ground. Okay, that's +2. Let's take a look at that. So from here to there is one. Let's take a look. Okay. So this now should be lead here. So lowering the overall reference. So from here to here should be the +5 that serves as the, or the -5 that serves as the common. Okay. And the next one up, so we just tied that one.
And then for the measurements, instead of measuring voltages at nodes relative to ground, just measure them relative to the negative.
Right, right. So when you simulate it, yeah, you can set up your supplies the same way too. So you can compare the voltages by subtracting or adding to them. I think that'll work. I'm just thinking, let's see, it'll be the same current. So it'll be the same current on the same side for the same resistor. The gate to source will still be biased the same way. An active region. And the source, drain source current should be the same on both sides. Yeah, I think it'll work. I don't see why not. Well, we can run a SPICE simulation. That's something to do. Test it out and take a look. Because basically it's a current source. So as long as we're creating the current, doesn't matter which rail we use. Equivalent current going in the right direction. Okay. Does everybody see what we did? So I could make a new schematic, for example. or I could use the same schematic. And let's go back. Let's see here. Let me go back to here and share that. So if you want your digilant to measure this current mirror, basically this is no longer ground. So you're going to have a negative 5-volt supply, that W, the V minus power supply attached here to give you 5 volts, negative 5 volts here at this point. And if you treat that as your reference now, instead of a ground 0 volts, but a reference, then on both sides, you want to apply basically a minus, what is it? This is 7 volts. So it's plus 2 volts here. So the total drop from here to here is going to be 2 volts. And then from here to here, another 5 volts. So that'll be 7 volts, or 2 volts relative to minus 5, which is 7 volts total. And on this side, you just leave it open at 0 volts.
Or connected to the ground of the digital.
Connected to the ground, yep.
Because current still needs to flow somewhere.
Right, so it's going in the other direction, so you still need the current. So you attach your ground of that V minus, or the ground, the new ground, up to this guy. So this guy's grounded. This guy's at plus 2 volts. And then you've got minus 5 volt reference here relative to ground. So then you have basically plus 5 volts through this one that's going to draw this current. And you have plus 2 minus a minus 5, which is plus 7 volts relative to the ground. I think it'll work. And just pulling the whole thing down. And it should give you the same currents, the same directions, the same biasing of the self-biasing of the Q1 and Q2, and they should both be in the active region. Does anybody see any flaw to that? Maybe what I should do is just print that out so you guys can see it and play around with it. And you can put it in the SPICE simulator, and then you can build a circuit and wire it up that way and test it for its to see if you get the same values for your currents that you do for. Any questions? So build your circuits as if you had 5 volt and 7 volt supplies and do your simulations. But then try that configuration where you bring what's right now 0 volts is right here, the common ground is right here, and bring that down by 5 volts relative to another ground. And then this is that ground, and this is plus 2 volts. So you can do the simulation both ways. And then when you'll see the voltage will be different, they'll all be offset, but the current should be the same. Make sense? But maybe I'll draw it up too, and I'll post it someplace so we can take a look at it. Yeah, and then you ought to be able to do this experiment with the Digilant. See what's going on with the BJT that Harry wants to try. No, that's way out of range. Yeah, unfortunately. That's plus minus 10 volts. You need a 20 volt range. That's the problem with the BJTs. But that gets to the point, like I wanted to show you guys this. If we got What did I do with it? Ah, here it is. Yeah. I'll turn on my camera here, show these to you. Okay, let's see. Okay. Okay. So does everybody see my my circuit layout, my breadboard? Yeah. So I found these online from Digilent, and they're basically little power bricks, and they attach up to your plus minus 5-volt supplies, and they've got up to plus or minus 9 volts, 12 volts. I don't think they go to 15, but this brick would allow you to get up to 12 volts basically for a lot of your circuits, which is basically a little DC to DC converter. And I'm going to start playing with these guys to see if they're can actually use them. I believe with these power bricks, we can do every single circuit in your lab. 332. Which is pretty cool. They're about, or you could build your own if you went and you purchased. So it would be in a little bit larger form factor, maybe if you purchased the DC to DC converter, and you could actually run it through a wall plug, wall wart, and get up to plus minus 15 volts. But I think these are fine because none of your circuits are high powered enough. I started looking at these because one of the capstone groups wants to create a DC to DC converter that goes up to 60 volts, I believe.
For what input?
I think I don't remember what their input was. But my proposal to them was, if you're going to do that project, why not build it for this? Build it for a 5-volt input. And it basically comes off a USB port.
How does it step it up like that? Does it like convert it to AC first, then use a transformer to step it up and then back to DC? Or does it just use a combination of diodes and capacitors or something?
I think the ones they were looking at is going to be a combination of transistors and large inductive circuits.
Interesting.
They would they would step it up to basically like a DC amplifier. Basically, is one thing they were looking at. I think I didn't see the actual circuitry, but I saw what they were talking about, and I was asking if they could use discovery modules to probe anything in their circuit. And they said, no, the voltage range is increased pretty high. Do not know what current they're putting out either. But I found some nice 15-volt DC to DC converters online that also I was thinking of using. I was talking to Arnie, maybe getting some of those. But these bricks are pretty nice, and they plug right into your board, and they're ready to go. You just you can use a single 5-volt supply, basically. So I'll play around with them, get back to you, see how well they work. Oh, I was going to show you the other breakout board. If you guys are still thinking of getting some accessories. All right. Well, that's what happens when you stay at home. The place gets messier and messier. It's due for a good spring cleaning right now. I can't find anything. Let's see what I got here. What's that one? Okay, here's a there's a lead and impedance analyzer I was saying earlier. Used to measure circuits with. You don't have to. I mean, you can use just the leads. It's a jumper for something else. And then we've got a bunch of these locked away at UW Bothell in the cabinet. And Eric was using these as a booster board. Basically wired his own, basically plus minus 15 volt supply comes off this board, plugs into the wall. And he also has some low speed DC coupled amplifiers on this board. You can switch different circuits in and out for different gain. So this would be useful for a lab, something like this also, if I can get the schematic and debug this one. But I think just the DC-DC converters, the booster, power bricks would be great. Breakout, what did I do with it? I'm going to show you that because that's really handy. I'm going to start using that. Put in the box here. Nope. No, I got some spring cleaning to do. I'll find it for you next time. Get you a part number. Okay. I guess before you get too bogged down in my own stuff, did you guys have any questions?
Yeah.
Sure. Go ahead.
Oh, not yet.
Oh, not yet. Yeah, go ahead and build your circuits. Don't hook them up unless you want to play with them. And I will post an addendum so that allows you to show you how you can measure them on your analog discovery 2 module, so you can take a look at that. And then we're going to meet on Saturday for those of you that want to or can attend, and we're going to do the LT Spice modeling of both the basic current mirror and the Vidler current mirror. And we're going to, in particular, we're going to play with the KN numbers and see what happens when we vary them, how our currents change, and then also to see what happens to if the 2 NMOS transistors have different KN numbers. Now, I've got KT sent me the email. I haven't looked through the parts list, but you guys have more than one 2N7000 MOSFET, right? Am I correct there? In your kits?
Yeah, we do.
I think it's like 4 of them, maybe.
Yeah.
Okay, good. Because that'll get us through the last lab. Also, I was just looking at that. But there is none in a 2 to a dip pack or anything like that. There's nothing like that, and there's no 2N7000. What is the 7002s or whatever they are? There's no IC with 2 of them on the IC or 4 of them on the IC.
Doesn't seem to be.
Okay, I didn't think so, because those would be better matched if we run into a matching problem. The 2N7000s are there in the kit because they're the cheapest ones out there. They're a factor of 4, something cheaper than the next one. Next NMOS device. Okay, I'm going to let you guys get going because you got class coming up 3:30.
Hey, Walt, I had a quick question.
Sure.
Me and a few of my friends are debating if we have to answer these questions or not. There are some questions on the lab report too, like ask like they're not in the like deliverables, but it's like within like the procedure. It's asking us like some questions, like for example, it's like what are the states of the capacitors at DC? Do we have to answer those and put those in the lab report, or those are just like questions that you thinking?
Yeah, just put them into your discussion and measurements technique. That
Okay.
Because the caps are basically setting up your bias circuit, right?
Yeah.
So they're basically opens. So you could say when analyzing the bias circuit to do this, to set the Q point or whatever, I treated the capacitors as open circuits, and therefore the biasing circuit looked like this, or looked like, like they were open or something.
Okay. Yeah.
And then when you did the small signal AC analysis, obviously they look like shorts. Or you can even add their impedance at 1 kilohertz into your model.
Okay. Yeah. Thank you.
Yeah, the 50 ohm source. I didn't see any difference between the high impedance setting on my function generator and the Digilant function generator for the sinusoidal signal. So I assume it's in a high impedance mode. So you don't even have to include the the 50 ohm resistor because you have it there in the analysis. But it seemed to be the same as the function generator, basically.
Okay, cool. Thank you.
Yeah. But yeah, just say the caps are, they're opens at DC, so the biasing circuit, they keep the DC bias from going out into the AC parts of the signal of the system. And if they serve as opens and the circuit looks like this, obviously, and then they serve at shorts or some really small impedance at 1 kilohertz, and therefore the circuit looks like this, and you have a small signal model for it. Okay. Any other questions?
Yeah. Hi, just another question for lab 2. You asked us to increase the input signal until it distorts.
Yes.
What distortion are you looking for? Are you looking for nonlinear distortion, or are you actually looking for actual clipping?
Well, they're all the same. They'll saturate on one end as opposed to the other. And the first thing you can look at is I saw it starting to distort. And that was the reason I went to such a low milliamps per volt squared, because I started seeing the signal distort even at 20 millivolts peak, right? And what I saw was the gain of the circuit that I built had, like, what was it, 15 or something like that. So even at 20 millivolts, it wasn't out to 300 millivolts on both sides. It was like starting to get clamped to 280 or something millivolts on one side and minus 300. And other people were saying they saw the same thing. And that effect kind of went away at roughly at 10 millivolts, certainly when it was gone by 5 millivolts. It was very symmetrical at 5 millivolts. It's inverted, but symmetrical. And the gain was consistent. So by distortion, it means that it's actually limiting, it's like compressing one half of the cycle, right?
Yeah, right.
Yeah, so that's what you'd see. And the easiest way to do that is just set it so your oscilloscope is AC coupled, right? And then you look at it, and it should swing an equal amount in the negative direction that it does in the positive direction. So if it was swinging to minus 300 millivolts, it should be swinging to a peak of plus 300 millivolts. And the first thing you see is the positive side starts to, depending where your bias point was in the Q point, it'll start to compress. It doesn't make it up to 300 millivolts. It makes it up to 280. And then the higher you go, it gets clamped there. It doesn't even look like a sinusoid. It looks like a sinusoid maybe on one side, and then the other side, positive side, it looks like a flattened sinusoid.
All right, cool. That makes sense. I was just a little bit, I got a little bit confused because you could have nonlinear clipping where, you just, it stops behaving linearly and you start seeing some.
So linearly, what linearity means is you have basically the same frequency at the output that you do at the input. So if you have a strict sinusoid with 0 DC offset at the input, and all the amplifier is doing is multiplying it, you still get a strict sinusoid at the output as well. But the minute that the output starts to compress, it doesn't go from, then if you took a Fourier transform of that sinusoid, you'd have more than one frequency component. So we'd have 1 kilohertz and maybe some other, something at 2 kilohertz. And that's what it means by nonlinearity. The circuit is no longer linear. So therefore, the frequency you put into the circuit is not the same frequency you get out of the circuit. You start to get additional frequencies due to the nonlinearities. So for amplifiers, that's very important, especially for Class A amplifiers that are very linear. Their linearity and their dynamic range based on their linearity is their biggest selling point. That's what you see in amplifier designs. You have a spur-free, the spurs being the nonlinearities, spur-free dynamic range of such and such and such a dB per hertz to the 2/3 or something, depending on the order of the nonlinearity. So like an amplifier, it's very common to see an SFDR, spur-free dynamic range spec, based on third order nonlinearities, or based maybe on a 1 dB compression point. And it's when you're putting in sinusoidal signals, tones is what they call them. You put in a tone, and it starts to compress the tone. That's compression. And you get other frequency components, harmonics. Or you put in 2 tones, and you should get 2 tones out, but you start the third order products and the fifth order products start to give you additional tones besides those 2 tones. Cross modulation, intermodulation, all these other tones start popping up. And that's what basically is Class A amplifier that's meant to operate linearly, has a limit into how high an input it can accept before it starts to, have those nonlinear effects on the output. And that's the maximum range it can go to. So that defines its dynamic range from the minimum signal it can see based on where the noise floor is to the maximum signal it can put out based on where the nonlinearities start to come above the noise floor. That's a classic way Class A amplifiers are analyzed. But in our sense, in our lab, where we see it, is it no longer looks like a sinusoid. It's no longer swinging from minus 300 to 300. It's going from minus 300 to 280. And then it gets worse as you increase the input. And those, if you did a Fourier transform of those signals, they're no longer 1 kilohertz signals. They're 1 kilohertz plus something, additional frequencies. distortion. That's what distortion is. Okay. I think class is at 3:30 today. We'll go ahead and take off, take a break.
Okay, hi. So today we're continuing the topic of, there's a small section left about current sources. And then we're going to start the next topic, which is about differential amplifiers. Any questions before we begin? Okay, so last time we talked about the two types or categories of enhanced or improved current mirrors or current sources, the Wilson and the Widlar. So this particular chart shows the BJT version of the Wilson. So it has an additional transistor compared to the basic mirror, and it has more accuracy in terms of mirroring the source, the reference at the output, and a higher output resistance, as we explained. The MOSFET version of the Wilson has the same architecture, 3 MOSFETs, so it has one additional MOSFET in relation to the basic pair that form a basic mirror. Then we moved on to the Widlar. This one has an added resistance in the emitter for the BJT. So if you don't put that resistor in there, then it's the basic mirror. By adding that, you made the Widlar source, if you will. And the main improvement here is the output resistance. And similarly, this is the MOSFET version. It has a resistance added to the source, and the output resistance is larger in comparison with the basic mirror with just 2 MOSFETs without the resistor. Okay, and then we looked at this one example. So let's open it. I have it in simulation. Let's see where that is. It's somewhere in there, right? On page 566. Okay. Example 8.6. So we have 2 different mirrors there with BJTs. One is the basic one, and one is a Widlar one. So this is the basic mirror. Okay. So we have a 10-volt source, and there's a 940K resistor that forms the reference, and then the 2 BJTs connected in a mirror configuration. Now we're going to look at the current through R1 and RO. This is the reference current, this is the output current. So we run a basic DC bias or operating analysis. So if you look at the output, that's 10 microamps, the current through R1, that's the reference current. And according to this, the current through the output RO is 10.4 microamps, a little bit higher. There's a beta factor that impacts this. But, the idea is to mirror the source. Okay. Now let's see. The second version of this is the Widlar version. Okay, so here you have that R3, which is the emitter resistor. This R2 is part of the reference. In that case, we make the reference current for the Widlar to be 1 milliamp, not 10, but the output, we expect it to be 10 microamps. And we worked out the numbers for the resistors. So if you run this and we're looking at the currents through R2 and R1, okay, R2 is 1 milliamp and R1 is 10 microamp, 10.36. So that's the Widlar simulation, and you get larger output resistance at Q2 here with the Widlar circuit. All right, let's go. All right, so that's what the simulation is, and then there is a picture of the Widlar here and the output. Okay, this is the third one, but we're not going to go in depth. Those two would suffice, but this is for just an overview. It actually looks a lot like the balanced Wilson circuit. Remember, there was a version of the Wilson mirror that you added another transistor to it to balance the voltage. So this is similar to that. It's a modified Wilson, maybe you can call it. It's called Cascode. And we have 4 BJTs. The reference is applied downwards from the left, and the output current is through Q4. Now, if betas are large enough, the currents through Q3 and Q1 will be the same, and then the currents through Q4 and Q2 will be the same. So the Q4 current is IO, and then of course the Q3 current is the reference current, if you ignore the base currents of the BJTs. There are some relationships here between the VCE voltages and things like that, but the bottom line here is you get also, just like the Wilson mirror, I think, right, or a beta over 2 factor improvement on the output resistance here in comparison with just the basic mirror that's formed by a pair of BJTs. So that's that. The MOSFET version is here for 4 MOSFETs, and the output is through Q3 and Q2, and the reference flows through Q4 and Q1. But we want to mirror the input at the output, so those currents would be the same. And doing the analysis here, which is not shown on these charts, but you get improvement in the output resistance by a factor of GM times RO. So that's significant expansion, if you will, of the output resistance. So there is some analysis, brief analysis done. We want to make sure this MOSFETs and BJTs are in active mode. So MOSFET active mode is the saturation mode. So we have conditions or constraints on the voltages, like VDS has to be greater than VOV to ensure operation in saturation or active mode. So based on that circuit and that type of analysis, this requires a minimum of, at the output of Q3, where it says V out, twice the VOV voltage of the, any one of these, but Q3 MOSFET plus a threshold voltage added to that. We need that much to ensure operation in saturation mode. Okay, let's do a brief example here, quick example, and then this will kind of be the end of discussion. We are skipping some sections from this chapter because there's so much time, and not everything is essential here. Let's see. Let's go to change the sharing to the pad. Okay. Okay. All right. Okay, so this one is an exercise about the cascode, which is like a Wilson mirror. Exercise 8-5. The analysis would be similar to Wilson. For a cascode MOSFET meter utilizing devices, so this is the MOSFETs have parameters VT equals 0.5 volts, and this Km prime is given as 387 microamps. Early voltage prime, this is per unit length, is given as 5 volts per micrometer. So that's something we are given, because otherwise you cannot find the output resistance. Output resistance becomes infinite without it. 3.6 micrometers and 0.36 for the length of the channel. Reference current in that 4 MOSFET circuit that we just saw is 100 microamps. Okay. First question here, find the minimum voltage required at the output and the output resistance of the, so basically, let me quickly draw this 1 and 2 like this. And then we'll do current source here. And then another one like this. And then another one like that. And this is output current. The voltage here is, you can consider that to be output voltage. These are tied together. This is usually grounded here. And then this is also like this, as if there are 2 basic mirrors here. Okay. And the output resistance is going to be that. Okay, so the first thing is we want this output voltage minimum. So that constraint is for operation in saturation or active mode for all the transistors, but particularly we're looking at Q3 here. All of these have to be in active mode, Q1 and Q4. So that result that we just were looking at earlier had that. So V out min equals threshold voltage plus twice the overdrive or excess voltage. Okay, we know the threshold voltage is 0.5 volt. We need to figure out what VOV is. So how do we find the overdrive voltage here? Well, we know the reference current. What is the output current? The output current, if the aspect ratios are the same for all MOSFETs, would be the same as the reference current. And that's 100 microamps. So now knowing the drain current or output current, we can find overdrive voltage because the MOSFET Q3, just like the other ones, are all going to be in active mode. So IO equals 1/2 Km prime times aspect ratio. This product of Km prime and aspect ratio is K sub n. That's process transconductance. This is VOV square. So that's how we get VOV. Okay, so this is, let's substitute here. Yeah, we can use microamps as long as it's the same everywhere. 1/2, this is 387 for Km prime. Aspect ratio is like 10, I think. It's 3.6 over 0.36 micrometers, but the units will cancel out. So let's do the numbers here. So it's going to be 100 times 2 over 387 times 10. Okay, and then I'll take the square root of that. So VOV itself comes out to 273 volts. Okay, then the minimum voltage needed at the output will be 0.5 volts plus 2 times the VOV 0.2273. So times 2 plus 0.5, it comes out to be about 0.955, about 1 volts. So that there should be at least that much voltage here, a 1 volt minimum, to maintain operation in saturation mode. Now, who's providing that voltage? Well, this current source is connected to another amplifier, which is not shown at the output, right? You can think of above it, there's another circuit here. But the amplifier has its bias DC power sources. So that voltage is coming from that other circuits, wherever the output is applied. So you would allocate at least that much to make sure the current source works. Okay. So that's the constraint. And then output resistance for this circuit is GM3, RO3, RO2. Okay, so all the MOSFETs have the same currents, same early voltage, same GM. So then we can find all these parameters, GM and RO2, RO3. Let's start with GM3. One way you can estimate GM is 2 times ID over VOV. There are other ways, but the results come up to be the same. I believe I have this on a formula sheet here. Yeah, 2ID over VOV. Or you can do Km prime aspect ratio times VOV. Or you can do square root of 2 Kn and ID. It's all equivalent. But then this is IO is the 100. All right, so let's make it 0.1 milliamps. And VOV is 0.2273. Okay, about 0.88, yeah, millisiemens. Okay. Now, to find RO3, we need VA, the early voltage. We divide by the drain current, right? IO. Okay, so we are given the early voltage per unit length, VA prime. So VA is VA prime times the channel length. Okay, so this is 5 volts per micrometer, and the length is 0.36. It's given as micrometers, right? So the early voltage is going to be 5 times 0.36, small value actually. .8 volts. Okay. All right. Then we can find this RO 2 and 3. So that's 1.8 volts. And then the output current is 0.1 milliamp. So that should be 18, right? A. And this is the same as RO2. The currents are the same. Everything is the same between the MOSFETs. So now to evaluate RO, we simply do multiplication, 0.88 milli times 18K, oops, times 18K. So this is milli, these are Ks. So we have to be consistent somehow. Let's do 0.88 times 18. So that's 15.84, but that's ohms. Now times 18K, that will be in K. So the end result is 285 kilo ohms. That's about right. Okay. Any question on this example? This is a MOSFET mirror, basically, like the Wilson one. So it gives us another example. Okay. Let's put this aside. We're gonna that concludes our discussion about chapter 10, current sources. Any questions on that? Anything about current sources? Okay. All right, now we're starting chapter 9. And that's about differential amplifiers. And then also in chapter 9, we're going to see multi-stage amplifiers and the operational amplifier example circuit. And this is the last major topic. There's one more topic after this, output stages. That's a different chapter, but we're going to do a basic overview of that as time allows. But this chapter will be in it for a while because multi-stage amplifiers are important, and the analysis is somewhat more complicated than just doing a single stage amplifier. What is this here? Okay, let me go back to the chart here. Sorry. Okay. So this is, the topic is differential amplifiers. Why use differential amplifiers? And first we're going to see what features they have, but then we're going to look at the circuits in detail and the properties. So differential is versus what some people call single-ended amplifiers or single-ended circuits. So the single-ended ones were the ones we studied in chapter 7, the common, the non-inverting, inverting, and the follower circuit. Those are all single-ended amplifiers, if you will, or circuits. They're not differential. And this is talking about differential amplifiers. All right. So the rationale for using this is that differential amplifiers have a lot more noise immunity at the input. So at the input of the amplifier, there's noise coming in. So this will, by nature, will block a lot of the noise, will prevent it from going into the amplifier, because if you allow noise at the input, it gets amplified at the output, then your signal becomes buried, basically. So this is the biggest advantage of this. Another one would be, as we will see, these amplifiers can be biased, and without having to put bypass capacitors or coupling or the blocking capacitors like we put in the discrete transistor amplifiers in chapter 7. This is important because capacitors are difficult to put in a large integrated circuit with many transistors. So it complicates life somehow, but it's doable. But if you can do it without using the capacitors, it's easier from the manufacturing standpoint. Okay, so this is something that you'll see in a lot of the different integrated circuits. The input of a circuit can be this differential amplifier or a differential circuit, like an op-amp, for instance, has that, as we will see later. So they amplify signals, but the signals have to be differential, and we will explain what that means. So it will have two inputs, like an op-amp, for instance, because an op-amp has 4 or 5 stages of amplifiers. The input stage is a differential amplifier stage for an op-amp, and then there could be 2 gain stages, 1 output stage, like the buffer stage, and this amplifies differential signals, but it rejects common mode signals. Okay, so we'll talk about what those are here, starting from now. So that circuit there on chart 5 is a differential pair, we call it, with MOSFETs. So there are two inputs. So the inputs are the gates of Q1 and Q2. And the output is at the drains, but we measure the output from drain 2 to drain 1, differentially we call it. And the input will be gate 2 to gate, or gate 1 to gate 2. So it will be the difference voltage, the voltage difference from one gate to the other. And the output will be the voltage difference between the two drains. That's the configuration for a differential amplifier. The two transistors in this circuit are matched, so it means they are identical. The drain resistors would be matched. Of course, you have one VDD. You have potentially a minus DC source, minus VSS. And that's that. So now we're looking at this same amplifier. You have two input voltages applied, and the voltage applied at gate 1 is the same as the voltage applied at gate 2, and these are labeled as common mode. So they're common at both inputs, if you will. And if this particular case is looking at the amplifier or the circuit when there are equal voltages applied at each input, if you will, gate 1 and gate 2. And then we will look at the output between drain 2 and drain 1, the voltage of one drain to the other. So this is the case where we have two gate terminals that are connected to a common mode voltage, where the two voltages are the same at each gate. All right. And of course, they're matched. Now, we have this circuit biased by a current source. So that I is a current source. So that current source is one of the circuits that we studied, or similar to what we studied just previously in chapter 8. So the square with a arrow is a current source, but the circuit of that is one of those mirrors. That's how this is usually, yeah. And then in this context, we're focusing on the amplifier here, the differential one. So we don't draw the mirror circuit in detail, but later on we'll see cases where you have the total complete circuit, if you will. But right now you just say, okay, I'll get a current there based on current source. So the biasing here is done by a current source, not by a voltage source, if you will, and a resistor. There are advantages to this, as we will see, by doing biasing with current sources. So in that differential pair, the circuits on the left and right are identical. So the current I divides equally between the two MOSFETs. So the drain currents, or the currents of Q1 and Q2, will be I over 2. If they're matched, there might be slight mismatches, but that's okay. Now, the voltage at the source, that source is common to both MOSFETs, V sub S, would be, if you did a KVL, you say VCM equals VGS plus VS, then the source voltage is VCM minus VGS on either side. But the biasing is done by the current source, and it splits evenly between the two MOSFETs, ideally. Okay, so the drain current for each MOSFET, which there will be the same, will be 1/2 Kn times VOV square. But the drain current is half the current of the source, so it's I over 2 equals to that. And of course, VGS minus VT is VOV, so that's the same equation. Then we can write VOV as I times, that should be L over Km prime W. There's a typo in there. That's what the notes indicates. So if we measure the voltage now at VD1 at the drain of MOSFET 1 and drain of MOSFET 2, we get, of course, VD1 is VDD minus RDID. And same thing for VD2 is VDD minus ID2RD. So of course, ID is half the current of the current source. So for each of the voltages now, you're going to get VDD minus I over 2 times RD. But in this case, the two drain voltages are the same. So the difference between VD2 and VD1, if you subtract one from the other, will be 0. So what this illustrates is that we apply a common signal at the two inputs. In other words, the input signals, when they are the same, then at the output, which is measured differentially, then you don't get to see any voltages. So that's the kind of what we were talking about earlier. If we have signals that are common or common mode signals, then that doesn't appear at the output. Everything is differential in this sense. Two inputs and two outputs, but then if the two signals at the inputs are the same, then the differential input is 0, differential output is 0. That's what this is. Okay, so now for this circuit, we have the voltages there. The maximum common mode voltage and minimum common mode voltage that this circuit can tolerate, if you will. So the maximum is okay, so it's the threshold voltage plus VD or VDS. Okay. So so the condition there is you want VDS to be greater than VGS or equal, at least greater than. So I think that's where that's coming from. VDS plus VT. That's VOV. Yeah, okay. Now the minimum comes from the requirement to maintain a certain voltage across the current source, like we just were talking about it earlier. Otherwise, the current source doesn't function as a current source. So that will be common mode signal. Okay. All right. So that's the minimum voltage that we can apply at the gate to satisfy the requirement for the current source. So you could go, you say VCM equals VGS, right? Plus the minimum required across the current source, which is VCS, that's current source, and then plus minus VSS, right? Now VG is threshold voltage plus VOV. That's because VOV is VGS or VG minus VT. Okay, so and previously it was similar, yeah. So this puts bounds on the how much common mode signal you can apply while the circuit rejects the signals. Okay, if you apply higher than that, it won't reject as well. Of course, if you apply lower than that, the current source doesn't work, then the biasing doesn't work. So it doesn't function properly. All right, so that's a basic idea of a differential amplifier. We will see the BJT version of this, but so far what we've seen is that when we apply voltages that are common to both inputs, gate 1 and gate 2, we measure the output between the two drains, but then we get nothing. So the common mode signals do not make their way to the output of a differential amplifier. So they're rejected, if you will. Or the circuit blocks the common mode signals or prevents the signals from going through. And we'll see why that is important. But let's start this here with an example, and then there's some more derivation and detailed discussions coming up. But the example gives us some feel of how these circuits operate. And then we'll explain the rest of the details, if you will. Okay. This is in beginning of chapter 9. Okay. On page 600 or 599, 598. Okay. So we are given a differential pair with MOSFETs with a common mode voltage applied as shown in figure that we just saw, 9.2. Okay, so that figure is this. So let me share the notepad. Okay, so this circuit is like this. We have two MOSFETs, one on the right and then one on the left. And we usually draw this like this. Their sources are common, and these are the VDDs for that. The biasing is done with the current source, and then this has minus VSS here normally. All right. Okay, so in that figure, it says put two common mode signals here, or apply two signals that are the same at each input. So that's Q1, let's say Q2. And then we're applying a voltage we would label as common mode at each input that are the same. Okay, let VDD equals VSS equals 1.5. So this is 1.5 and this is minus 1.5. DC sources. All right, the parameter transconductance is 4 milliamps per volt square. Threshold voltage is 0.5 volts. I being the current of the current source is 0.4 milliamps. And then the drain resistor is 2.5 k ohm. So each one of these is 2.5 kilo ohms. So they're the same. The two halves of the circuit are identical. Neglect channel modulation. It says, assume that the current source requires a minimum voltage of 0.4 volts. So that's the current source requirement to have at least that much to operate properly. Okay. First part, it says find VOV and VGS for each MOSFET. They'll be the same. These are identical MOSFETs, and everything else applied is the same. Okay. So again, everything is operating in saturation mode, and so we can find VOV by knowing what the currents are, right? And the parameters. So this is ID1, ID2. So the currents in each MOSFET will be half the current of the current source. So that would be 0.4 over 2. And that's 0.2 milliamps. Okay. Now we can say that the current of one of the MOSFETs equals, they're in saturation mode, 1/2 times Kn, which is 4 milliamps per volt square, times the overdrive voltage square. So from this, we could estimate the overdrive voltage. Okay, 2 times 0.2 over 4. And then we'll take the square root of that. 0.3162 volts. And what's VGS? VGS is going to be VOV plus VTN, because VOV is VGS minus VTN. So that would be 0.316 plus 0.5, because that's the threshold voltage. Okay, 0.816 for VGS. That was part A. Okay, part B. If this applied voltages are 0, VCM is 0 on each MOSFET, then find the source voltage, the drain currents, and the drain voltages. So ID1, ID2, VD1, and VD2. All of these. So to get the source voltage, so you can think of this like this, right? On one of the MOSFETs. Now okay, so there's 0 volts here, so that's like that. And this is the source voltage at the source. Okay, gate and source. So, all right. Well, we know that VGS is equal to what? It's VG minus VS, right? But the gate voltage is 0. So that's minus VS. So then VS is going to be minus VGS, but we know what that is. So it's going to be 0.816. Okay, so that's going to be, for this condition, that will be the voltage here at the source. It's going to be based on what's applied at the gate, and then minus the gate to source voltage. Okay, so what will be the drain current now? Well, in a circuit that has a current source, so the current source dominates or dictates what current should flow, basically, right? So those currents are still going to be the same. The drain current will be half the current source current. They'll be 0.2. They don't change. And VD1 equals VD2. So that's going to be VDD minus RD times ID1 or ID2. That's 0.2 milliamps. So 1.5 minus 2.5 times 0.2. So that's going to be about 1 volts according to my calculation for the drain currents and voltages at the drains. I think that's that. Part C says repeat part B. For this time, apply plus 1 volts at each input. Okay. Now, so you can see that's the picture above, right? VCM here. This voltage is VGS plus VS, right? So the only thing that's changing is the gate voltage. So that VCM equals VGS plus VS, right? So that means 1 volt equals gate to VGS was 0.816. Now the source voltage will be 1 minus 0.816, 0.184. All right. Now, what about the drain currents and the voltages at the drains? Those stay the same. So they're not impacted because the current is half the source current, and then the voltages at the drains would be VDD minus RDID. So ID1 equals ID2 equals 0.2. And then VD1 and VD2 are 1 volts each. So those do not change. Okay, there's a part D like that with the negative voltage, but the calculations are the same. So let's just skip over that. You can do it. It's easy. It's done. Part D, let's keep it here. Part E. What is the highest permitted value of VCM? So this is VCM max for the proper operation. And then part F is asking for VCM min. So if you look back, those were in the charts. All right, so VCM max was VT plus VDD minus ID or I over 2 times RD. And then that's in part E. This is in part F. It's going to be VCM min, which is minus VSS plus the voltage required for the current source plus the threshold plus VOV. Okay, so all right, I Okay, I think we're seeing this, right? Yeah. Okay. So this is from this problem, this was 0.5. VDD is 1.5. I over 2 is 0.2 milliamps. RD is 2.5 K. So actually that's 1.5 minus 0.2 times 2. That's 1 volts. Plus that it's 1.5 volts basically. That should be the max that we need, or it can go up to VDD, I guess, at the input, at the gate. This is minus 1.5. 0.4 is required for the current source. This is 0.5, and VOV is 0.316. So this should come up to be a smaller number. Minus 0.284 is what I get. And then, yeah, that's as low as we can make it, the input voltage, without compromising the operation of the differential amplifier, and it can go as high as 1.5 volts. So that's the input range for common mode signals of that differential pair or differential amplifier. But that's only part of the story. Okay, so so far we just applied a common mode signal, and then we didn't see any of that at the output, at least when we measure the output differentially. So that's where we are right now. And then any questions on this? Okay. All right. Now, when this next discussion will focus on when we apply differential inputs. In other words, the two input voltages are not the same. So when you measure the difference, you get a differential signal, if you will. So the picture on the right now has a voltage applied at input 1, but gate 2 is at ground. So there's a differential signal between gate 1 and gate 2, which is VID, we call it. That's differential. I mean, you can have two signals there too. If they're not equal, the difference would be VID. So VID is VGS1 minus VGS2. In this case, VID is applied at the gate of Q1. So that implies that VGS1 is going to be higher than VGS2. And with all else equals, the two MOSFETs are matched, the drain current would be significantly larger than in Q1 than Q2, the way that signal is applied. If we applied a higher signal at the gate of Q2, then ID2 will be higher than ID1. Okay, so, and if the currents between the MOSFETs are not the same, then the voltages won't be the same, and the difference would be non-zero. So this means that this circuit allows differential signals at the input, and you can see that at the output. Okay, so there are some derivations here. We're going to go through them as much as we need to just understand the concepts. Some of these derivations are lengthy, but important is what's important is not the actual derivation, but what comes out of it. All right. So this first question here on chart 11 says, what value of that differential signal, how much of that do we need so that all the current of the current source flows in Q1 and there will be nothing in Q2? So always the current I is whatever current is in Q1 and Q2. So they're not the same when the input signals are not the same. But at one extreme end, you can have all the current of the source go through Q1 and nothing go through Q2. So then we know that if that's the case, if ID1 is the current of the current source, which means ID2 will be 0, then I equals 1/2 Kn VOV square. And then from this, we can get VGS equals VT plus the square root of 2 times I over Kn. Or that's VT plus square root of 2 times VOV. Okay. So the maximum voltage differential, if you will, in this case, it's applied at Q1, is of course, the VID is VGS plus the voltage at the source, right? In that condition. Now, let's see what the voltage at the source will be. So VS plus VGS2 is 0. If you do the KVL around the gate and source of Q2, so you get VGS plus VS equals 0, right? Okay, now in this condition, we said ID2 equals 0. So that's Kn over 2 times, that should be square there, VGS2 minus VT square. But anyways, if the current is 0, then VGS2 will be equal to threshold voltage. That means that if VGS2 is equal to threshold voltage, then the source voltage would be minus the threshold voltage. So then you get to take that result and apply it to the max VID on the left. So where it says VGS1 plus VS, so we substitute minus VT for VS, then you get VGS1 minus VT. But VGS1 from above is VT plus square root of 2 VOV. So the two VTs cancel out, then you get square root of 2 times VOV is the. So if you make your differential signal to be the square root of 2 factor times the VOV, then you force all the current to flow in one MOSFET. That's what this is saying. Okay, now this next few charts are derivations. So when we have a differential signal applied, there will be currents in each transistor. They won't be equal. But of course, if you apply higher voltage at one of them, that transistor will have the higher current, but the other one will still have some current, depending on how much your input signal is. All right, so basically, we assume matched transistors, meaning that the KNs and the VTNs and everything is the same. We ignore the channel modulation here. All right, so ID1 will be 1/2 Kn VGS1 minus VT squared. ID2 will be a similar expression, right? VGS2. Now, VGS1 and VGS2 are not the same because there's a VID applied. There are different gate voltages applied. Now, you take the square root of those currents and you get those results and on the right. Now, we do know that VGS1 minus VGS2 is VG1 minus VG2. And that's going to be what we call VID, is the difference voltage or differential input voltage, which is the difference of the two voltages that are applied. And VG1 and VG2 are not the same. If they're the same, that would not be differential. That would be common mode if they're the same. So differential mode means there is a difference between those two input voltages. So going back to those equations, then we subtract the second equation from the first one, and then we substitute VID equals VGS1 minus VGS2. So when you subtract the two, you're going to see VGS1 minus VGS2 there. Then you put VID in there. And basically, it's going to be square root of 1/2 Kn prime aspect ratio times VID. It's easy to do that math. All right. Now, we always have to have I equals ID1 plus ID2, because the current source current will be divided somehow between the two drain currents. That's based on Kirchhoff's current law. So we take that equation that we just had, we square both sides, and if you square that equation, you get ID1 plus ID2 minus 2 times the square root of ID1, ID2, right? Okay, then ID1 plus ID2, we substitute that with I, then that equation becomes this next equation that's shown here. So it's simply square both sides, then substitute ID1 plus ID2 equals I. Then we get this result. Then here we substitute ID2 equals I minus ID1. So then you solve for ID1. Oh, okay. Because if you substitute for ID2 equals I minus ID1, you have one equation in ID1. You would manipulate that equation, somehow square it such that you get this expression. Yeah, squaring both sides, and you get a quadratic equation in ID1, which you solve, then it will give you the solution that we have. So there are some steps here. We are kind of jumping around ahead, if you will, a little bit, but you can go through the derivations if you want. So that gives us an expression for ID1 in terms of I, which is the current source current, VID, which is the input differential signal, and the MOSFET parameters. Then we can do the same for ID2. It's a similar expression. And that's basically the two equations. Now, if we have no differential signal applied, okay, then basically VID becomes 0. Then ID1 equals ID2 is I over 2. That's what you get, because the terms on the right they zero out. So you get I over 2, and VGS1, VGS2 would be the same as whatever voltage, DC voltage you had when you're biasing the circuit. That's what that's saying. Now, taking these equations and further manipulating the equations. So, like, if we take I over 2 equals 1/2 Kn VGS, it's that. Replacing Kn prime times aspect ratio with I over VOV square, because that's the relationship that holds in the saturation region. Then what ends up being now is everything in that equation now you're adding a dependency on VOV. So the two equations at the bottom left, after you substitute that Kn prime times aspect ratio equals I over VOV square, then you get to see that VOV in the denominator. So then you have VOV here, you have VOV here, and then you get ID1 and ID2. So the two equations that we have here are strictly functions of course, the current source, the overdrive voltage, and the differential applied voltage at the input. That's where we end up now with these two equations. So we will use these results now to see what impact the differential signal has in terms of the operation. Okay, all right. So we plot each of these currents in terms of VID. So ID1 and VID can be from minus 1.4 to plus 1.4, which is square root of 2 times VOV, because that's the limit. So when ID1 is negative, when VID is negative, then ID1 is 0. As you increase VID, ID1 increases. Okay. And then you can see as ID2 is maximum when VID is negative. That's just the way the formulas work. But as we increase VID, ID2 drops. The two meet at that middle point there. That's where the two currents are the same, and that's I over 2. Okay, and if we further increase VID, then you can see ID2 further increases, and ID1, and ID2 drops. This is a normalized current of the drains over I, basically. All right. So if you increase VID, at some point you see the curve tapers off. So there's a linear region in the middle there, but then it becomes nonlinear at the edges. Okay, so these are called transfer characteristics, and there are nonlinearities there. But we can operate this because it's an amplifier again, as we will explain further. We want that to be linear. In other words, you want the gain to be predictable. So if you look at these two equations, then if ID1 is I over 2 plus this term times square root and then VID square inside, right? The nonlinear terms are the ones that are inside the square roots, the second order terms. So if you minimize the terms inside the square root, or make it 0, let's say, then you get linear straight line type equations. So how do we minimize 1 minus VID over 2 over VOV square? Well, if we choose VID over 2 to be much smaller than VOV, then the expression inside the square root of 2 becomes close to 1. So then the equations becomes ID1 equals I over 2 plus 1 over VID over 2. And ID2 is I over 2 minus 1 minus I over VOV times VID over 2. Now, these are linear equations. So that means if this condition is met, the condition for the differential signal to be less than the VOV by a big margin, then you can say the circuit is linear. And these are the expressions for the currents. Now, I over 2 is the DC current, bias current, right, from the current source. So, and then, which means that 1 over VOV times VID over 2 is the so VID is a small signal, differential signal. It's AC if we represent it as lowercase. So the small signal component of ID1 and ID2 will be 1 over VOV times VID over 2, because I over 2 is its DC component, the bias. Okay, so these two equations for ID1 and ID2 are plotted here for different values of VOV. So you see there for ID1, let's say over I, we have VOV equals 0.2, 0.3, 0.4. As we increase VOV, you can see that the linear range of the current ID becomes wider as you increase VOV. So this can be achieved by lowering the aspect ratio of the MOSFET. But if we did that, then your GM, which is proportional to the aspect ratio, because if you look at the equations for GM, so it's Kn times aspect ratio. So there's always it's proportional to the aspect, but the GM parameter goes down. And as we have seen for the amplifier from chapter 7, the gain of the amplifier is a function of this GM, and this amplifier also will have a dependency. The gain of this will be dependent on GM. So if you lower the aspect ratio, you increase VOV, but you increase the linear range so of the circuit, but the gain becomes lower. So there's a trade-off here. This is similar to what we were talking about in the common emitter and common source when you put a resistor in the emitter or the source. So you improve input signal range, but at the cost of gain. It's a similar trade-off here. Okay, so that discussion is basically saying, okay, we would apply differential signals, but we want to make those differential input or the difference of the two signals, small signal AC, to be considerably lower than VOV to maintain linearity, proper operation for the differential amplifier. And yeah, and of course, if you want to increase the linear region, you can increase VOV, but at the cost of gain. So those are the two things here. And these are equations that give you the currents when we have a differential signal applied or when the two signals are not equal at the inputs. Now, this is formalizing a method for differential signals and common mode signals. So one way to do this, of course, the differential signal, if we have two inputs, right, and V1 and V2, right? So the differential signal or the difference signal is always the difference between the two. So that could be represented as V1 minus V2. Now the common mode signal can be the average of the two. That's a representation, V1 plus V2 over 2. Okay, so then you can use those two equations and solve for V1 and V2. You get V1 equals VCM plus VID over 2. V2 equals VCM minus VID over 2. So V1 and V2 are your input signals to the differential amplifier. So what these two equations are saying, the way they're represented now, that we can have signals that are common to both inputs. That's VCM. But we will have a differential signal VID, and we can say, okay, on input 1, it's going to be VID over 2. We can put minus VID over 2 on input 2, make V2 to be minus VID over 2. But again, if you subtract V2 from V1, we still get the VCMs cancel out. VID over 2 minus VID over 2 is VID over 2 plus VID over 2, it's VID. So the difference between V1 and V2 is still VID. And yeah, and then they have common mode signals that's common to both inputs. So you can think of it like that, the two sources, VID over 2 minus VID over 2, where minus VID over 2 is flipped, and then VCM is common. So V1, V2 are the two inputs. This is another way of looking at the differential signals. Okay, so this is back to the differential pair with MOSFETs. So we have two inputs, VG1 and VG2. So in both of these signals, we'll have a common mode signal that's common to both inputs. And we will have VID over 2 on the left and minus VID over 2 on the left, such that when you take the difference, you just get VID between gate 1 and gate 2. And if you're taking the difference, the common mode signals cancel out. So that's, and then those are shown as in blue also on that figure. And you also see VD1 and VD2. And the difference between VD2 and VD1 is VOD. I don't know if you can see that, but it's okay. It's shown there. Okay. Well, that's as far as I can make it. That's VOD. It's VD2 minus VD1. When we have a VID, or there's a difference voltage at the inputs, we're going to have some difference voltage at the output because the currents are not the same and the voltages at the drains are not the same. Okay. Now, this is looking at the small signal models of the differential pair with MOSFETs. So you have drain and drain 1, drain 2. This is the T model of the MOSFET. So there is a current source between drain and gate. There's 1 over GM between drain and source. All right, now we're constructing the small signal model. The current source I is DC, so you open circuit that, you remove it. VDD gets grounded. So that's what we have. And now, and then of course the common mode voltages are not shown in the small signal model. So then you have VID over 2 plus at the gate of MOSFET 1, if you will, and minus VID over 2 at the gate of MOSFET 2. So Okay, so the way this is shown now, since we have a negative voltage at the gate of MOSFET 2, so the current is showing moving upwards. So basically the small signal current in MOSFET 1 flows downwards, okay, but then this current in MOSFET 2, which kind of rolls around, if you will, from MOSFET 1, goes upwards because the voltage is negative there at the gate, so the current flows upwards. So VID over 2 at the gate of Q1 means current goes downwards into 1 over GM, right? And that's the current source direction. Now, minus VID over 2 at the gate of MOSFET 2 means that the current has to flow opposite. And then the current source is showing that direction of the current going upwards. Okay, let me see here. Yeah, okay. Yeah, we can look at this here. Okay, so let's do a KVL here around, well, the current in MOSFET 1 in Q1, it's GM times VGS, right? But VGS is VID over 2. Same thing for the current in MOSFET 2 is GM times VGS, but it's moving up. So the voltage at drain 1 is going to be RD times ID with a minus sign. And the voltage at drain 2 is the current times RD with a plus sign, because the currents are opposite. The resistances are the same. So we do a KVL now where VID over 2 plus is, and we go around MOSFET 1. So VID over 2 is the voltage drop across that 1 over GM on the left, and that's the current, which is GM VID over 2 times 1 over GM plus VS. So that's KVL around the gate to source of Q1. Okay. Now, if you look at that equation, the GMs cancel out. So you end up with VID over 2 equals VID over 2 plus VS. So that means that small signal VS is at 0 potential. This is what we call a virtual ground. It's not a physical ground, but it ends up being that you have 0 volts there, according to that analysis. All right. So now here is where we're looking at the voltages at the drains, or output 1 and output 2. The output 1 is going to be the current, which is GM VID over 2, times the resistance, but with a negative sign because the current is opposing the convention for VD1 or V output 1. V output 2 or VD2 will be just the current times RD. Current is GM VID over 2. So you get VD1, VD2, V output 1, V output 2. Okay, of course, we know GM is 2 times ID over VOV, or etc. Now, the input signal is differential, VID. The output is measured differentially, drain 2 to drain 1, output 2 to output 1. So VOD, which is the differential output or the output, is VO2 minus VO1, VD2 minus VD1. So VO2 is GM VID over 2 times RD, minus VO1, minus becomes plus, so that GM VID over 2 RD. So then you add up those two terms, you get GM RD times VID. The gain of this amplifier, the differential gain, because it only has a differential gain here for so far, because we assume that there's no common mode gain, at least in the ideal case. So VOD over VID is AD, that's different for differential mode gain. It's VOD over VID, it's going to be GM times RD. So the conductance times the drain resistance. So that's the voltage gain of this differential amplifier. But of course, we're talking about differential inputs and differential output. So, because if the signals are equal at each input, and we call those common mode signals, and we measure the output differentially from drain 2 to drain 1, then those would not have any output voltages. So those are not are rejected, basically, the common. But this is for differential inputs where the two signals applied at the two inputs are not the same, or you have some signal applied here and nothing there. Either way, you get the difference is what gets amplified. That's the takeaway from this discussion here. Sometimes, so you look at this circuit and you can see there are two circuits inside. You can basically use the half circuit analysis. Sometimes that's done. You'll see it in the book. Just to keep that in mind. Okay, this is the half circuit equivalent, if you will. If we did the analysis based on the half circuit, then we would show it like VID over 2 and then VOD over 2. But sometimes we'll see this done when we have large circuits. They only use half of it. But if you use the whole circuit, that would be fine too. But if we account for the early voltage in the differential amplifier, right, that amplifies differential signals, then your equation that was GM times the drain resistor would be GM times the drain resistor in parallel with RO, because RO would show up in this model, right, between drain and source. Now, this discussion analysis did not account for RO originally, but if you put an RO in there, the result would be GM RD in parallel with RO. Just like if you connect a load, then you'll have a different gain. That's what that's saying. Okay, there's another way to do these amplifiers. Okay, so the original method of the differential pair that we saw has two MOSFETs, two drain resistors, one VDD, one minus VSS, and there's a differential input that gets amplified, right? That's shown on the left. There's a current source that biases the circuit. Now, okay, so in the circuit on the right, you replace the drain resistors with current mirror load, we call it in this case, because it's not actually acting as a source. So basically, you're replacing RD with a transistor and another RD with another transistor. The gates are connected together. So that's now the lower portion of the circuit is still the same. The differential amplifier, you can see where the output is VOD as before. But the drain resistors are replaced with two MOSFETs where the gates are connected. So that's like a current mirror load, if you will, they call it. And this is done because in integrated circuits, it's easier to integrate MOSFETs than resistors. Resistors can become inaccurate, they take more space, but that's not the only reason. Doing it this way, in other words, instead of using resistors for the drain, at the drain, we put MOSFETs, then the gain will be much higher with the amplifier shown on the right that has a mirror load, if you will. So basically, it ends up being that if you did the small signal model of this amplifier that has the current mirror load, right, then you get RO1 and RO3. Okay. Okay, so the derivations of this is not shown in the charts, but basically, in the small signal model, when you drew this and you put T models for all 4 MOSFETs, you will end up getting a gain of GM, and then the MOSFETs will have RO1, RO2, RO3, RO4, but the drains are grounded, and so then those RO1s and RO3s, for instance, or RO2s and RO4s are going to be in parallel. It ends up that the gain becomes GM1, RO1 in parallel with RO3. Now, that's the same as GM2, RO2 in parallel with RO4, because all 4 MOSFETs are matched. Well, I mean, Q1 and Q2 are matched, they're NMOSs. Q3 and Q4 are PMOSs. So the current mirror loading is done by PMOSs. And you get a gain like this. So basically, what we had when we used the drain resistor, okay, so with the differential pair, we had GM times RD in parallel with RO, right? Okay, now if we replace the drain resistors with 2 PMOSs in a current mirror load configuration, then you get GM times RO in parallel with RO. So GM and RO, 1 RO are the same, but then instead of RD, you're putting another RO here. RO is much larger than RD. So RO is strictly dependent on the early voltage and the drain current. So usually it's on the order of 100K, 150, 50K, but the drain resistor is like 10K, right? So doing it this way, and this is done in integrated circuits because it's easier to integrate many MOSFETs than putting resistors and capacitors and other things. Then also we get a larger gain, a significantly larger gain that way. So it's the same differential amplifier, but the load or the drain resistances are substituted by MOSFETs. And the MOSFET there has an RO as a resistor. Okay. So that's that. Now, I think the next topic we're not going to start. Let me see here if there is an exercise we can do. That's the differential. Okay, let's try this exercise 9.4. And then we'll do one yeah, that should be sufficient for now. Okay, exercise 9.4. This is on page 611. Okay. A MOSFET differential amplifier is operated at a total current. So this is MOSFET differential amplifier. Sometimes they call these diff amps. And it has a total current. So that's basically the current of the current source of 0.8 milliamps. It uses transistors with aspect ratio of 100. And this mu n COX, this is Km prime, by the way. It's 0.2 milliamps per volt square. Okay, early voltage is given as 20 volts. The drain resistors each have values of 5 kilo ohms. Okay, so this is back to this amplifier, right? All right, and then here we're going to have a current source. Okay. I 0.8. The drain resistors are both 5Ks, 5Ks. And there's VDD here to bias. All right. Okay, so the implication here is that we have a differential input here because they want us to find the gain. So you can think of it that there's a signal here, that the difference signal between the two inputs, VID. And the output here is VOD. Okay, so for a differential amplifier, it amplifies the difference between the inputs, because if the inputs are the same, that doesn't get amplified, that gets rejected. So you can either put V1 and V2 here, or just put one V on here and ground the other one, or sometimes you see the voltage from gate 1 to gate 2 as being just one VID. That's differential input. And these are not connected. That's what that means. The current source is for biasing. And the DC sources also. Okay, so that's what we're given. Then it says to find GM, which is the conductance, RO for each MOSFET. They will be the same. They're matched. And the gain, differential gain. Okay. Okay, how do we find GM? Well, the current of each MOSFET, right? ID1 or ID2, right? You can do it either way. It's I/2. Because this current, the DC portion splits evenly. It's going to be 0.8 milliamps over 2. That would be 0.4 milliamps. This is DC. That's a DC source. Okay. Now, we know that ID1 or ID2, this is ID, I'm calling it. Each MOSFET, whichever one you want to do, doesn't matter for DC calculations. It's going to be Km prime over 2 times aspect ratio times VOV squared, right? I think to find GM, we need to find VOV first. That's what I'm thinking here. 4.4 milliamps equals, this is 0.2 milliamp per volt square over 2 times 100 times VOV square. And that's the same for both MOSFETs. So that's 2 times 0.4 over 0.2 times 100. And then we'll take the square root. So VOV is 0.2 volts. Okay, now you can do simply GM equals ID over times 2 over VOV. Or you can do KN times VOV. Either one will work. So that's 2 times 0.4 milliamps over 0.2 volts. So that's going to be 2 times 0.4 over 0.2. About 4 milli Siemens. Okay. All right. So that's GM. And we have VOV. And we have GM. All right. Now let's do RO. How do we find the value for RO? It's the early voltage divided by the drain voltage, right? Okay, so that's 20 volts over the current of the MOSFET, and that's 0.4 milliamps. This is 50K. All right. Now you go back to what we were saying earlier. So the differential gain, which is differential output VOD, which is shown in that figure, it's from drain 2 to drain 1, over VID, which is from gate 1 to gate 2. All right, so that's equal to GM, the GMs are the same, times RD in parallel with RO. And RDs are the same, ROs are the same. So this is 4 milli. RD is given as 5K. RO is given as 50K. So we do 5 in parallel with 50K. Then we get about 4.5K. And we multiply that by 4 milli. That will be the differential gain. And I'm getting 18.18. 18.2. Okay. So this is the basic MOSFET differential pair, or what we call differential amplifier with 2 MOSFETs. So it has a gain. It amplifies differentially applied signals, or the difference of the 2 signals, if you will. And by 18.2 times, it rejects, or it doesn't amplify signals that are common mode. So that's kind of the takeaway from this. There's some more derivations as we look some of this, but don't need to go in depth into those. It's important thing is to understand the concepts, underlying concepts, and what the results mean. So common mode signals, on a differential amplifier, we don't apply those ourselves. We don't intentionally apply common mode signals. Those are inadvertently applied by noise. Those are noise signals that get coupled to the two inputs. So your circuit is built somewhere, and there is noise coming from the ambient or somewhere else through the power line or whatever. There's something else going on in the vicinity. There's noise coupling to your circuit at the input. So the chances are that the noise would be the same at both inputs, right? Because noise doesn't discriminate in that sense. It gets applied across the board. So, but then at the output, we don't get to see the noise, which is a big plus. If you had amplified the noise, then you're going to see so much noise at the output that you can't see your differential signal at the output. So this is the advantage of the differential amplifier. As we said earlier, it rejects noise, which noise is a common mode signal by nature, and it provides a gain, and it doesn't require capacitors to block at the input and output. That's another advantage, but the biggest one is the common mode noise rejection. Okay, so that's the end of the discussion for today. Any questions? Any comments, anything? We haven't heard anything from anybody today, so I don't know.
Not really.
Pardon?
Not really.
Okay.
I don't know if you talked about this and I just spaced out, but why don't we need capacitors in these amplifiers that are not shown to separate like DC bias or
Okay, good
AC?
question. Yeah. So yeah, so the input is AC. So we're not putting capacitors in there. Okay. So the DC bias of this is in the middle, right? Where the VDD is RD transistors and VSS, right? So we have DC. Okay, the input is at gate 1 and gate 2, right? So if you have DC here at gate 1, you're going to have the same DC at gate 2. So they don't amplify in that sense at all. And I'm trying to think here if that input AC signal that we applied differentially, so it's going to have a DC here and it's going to have the same DC here. So the difference, the potential voltage does not appear across the input source. The DC doesn't appear because this is a differential signal at the input. The DC values are the same. The DC voltages at the gate are the same. So technically, you don't get the DC to be applied at the input signal, or the input doesn't care, if you will. Maybe that's how I should phrase it. And at the output, now again, this in general, differential amplifiers and those amplifiers we saw in chapter 7 are connected to other amplifier stages. We don't normally use a single stage. So at the very output, then we'll have a buffer circuit, and then potentially we can put a capacitor in the output just to isolate the speaker or the load, if you will, from the differential amplifier. But between stages, we don't need to put capacitors.
Okay.
So
and this is assuming that the MOSFETs are matched, right?
Right.
Like if they were slightly off, then there would
Right.
be like a DC shift.
Yeah, we'll see that next time. If there is a mismatch here, then you get some common mode to trickle through from the input to the output. And you might see a small DC component at the input source. Now, if that bothers you, you can put a capacitor, but that's going to be external to the amplifier, right? At the input side, you can still do that. But it won't be within the amplifier, and then this amplifier is connected to another one. You don't put capacitors in between. You don't have to, okay? Because when we do integrated circuits, but if you build these circuits yourself, you can put capacitors. Those are easy to put on your own. But in an integrated circuit, capacitors and resistors we try to avoid because they take more space, plus their values are sometimes they're not determined properly, if you will. So we put MOSFETs are generally, I mean, by nature, they lend themselves to integration very easily. But we try to avoid resistors and capacitors. And of course, you don't see an inductor at all. So in this electronics, because inductors are notorious in terms of space, even more than capacitors. Capacitors can be miniaturized. Inductors cannot. So on a circuit board, if you can avoid inductors, you would, but sometimes we cannot, and then we put in an inductor. But so far in these circuits, they omitted inductors on purpose.
Okay.
Yeah. But those are good questions. Yeah. Anything else? So I think that's it. So we're going to have a homework due Monday. Few problems from chapter 8, basically about the basic mirrors, BJTs and MOSFETs, and then the enhanced mirrors, the Wilson and Widlar, both MOSFETs and BJTs. The cascode, it's there. I look at it as that's like a Wilson, balanced Wilson, yeah, or two mirrors added together, if you will. So mostly the Wilson and Widlar are the focus, and of course the basic mirrors too. And those mirrors, like we just seeing a current source here, one of that current source is coming from a mirror. There's a mirror circuit in there that's we're not showing yet. But when we do the differential multi-stage amplifiers, you will see sometimes we put this as symbols, but sometimes you also show the detailed current source circuit in there too. So because technically you have to build the current source circuit, somebody has to. Yeah. But for simplicity, we show symbols here, right? And sometimes we don't show all the details of the current source, but there is a circuit behind it. Okay, I haven't graded the exams yet, so this is my task to do here. I started it, but it will take me probably the whole weekend. Hopefully by next week you'll get it. All right, have a good rest of the week.
Thanks, you too.
Yep.
Thanks.